Thank you, Misha. Please have a seat. We'll have also our previous keynote speaker, Edward Knightley, here on the panel, and Josep Hornet. He is a professor in the Department of Electrical and Computer Engineering, the director of Ultra Broadband Nano Networking Lab, and associate director of the Institute of Wireless Internet of Things, and a faculty member of the Smart Center at Northeast University. His interests are in terahertz communications, wireless nanobiocommunication networks, and Internet of Nano Things. He's a fellow of the IEEE and is currently the IEEE Communication Society Distinguished Lecturer. Please have a seat. It's over there. All right. I'll start by stirring the pot a little bit. So, Edward, you talked about communication about 100 gigahertz. Misha, you emphasized the importance of midband. So my question is, what's up with millimeter wave? So just a few news articles I came across. And this body has been working on millimeter wave for a long time. There has been standardization efforts, deployment efforts. But it looks like South Korea, for example, which has been on the forefront of millimeter wave, the regulator recently revoked licenses for millimeter wave because of lack of deployment. And a recent statistic from Global Mobile Suppliers Association showed that just 9% of all announced 5G devices has millimeter wave on them. So there are some mixed reports coming up, and we know that deployment takes time, evolution takes time. But I think this is a good point for a reality check of where we are in millimeter wave. So I'll start from research perspective and ask about, with all the research we have done and you have also done, maybe Edward, we can start with you. Where are we in millimeter wave? What do we know that works? What do we know that doesn't work? And what do we not know?
Okay, sure. Normally I would say thanks for the question, but I don't know if I'll start with that. But let me say, so my focus has primarily been on the Wi-Fi part of it, so I'll comment more on Wi-Fi and then the research. So as all of you know, Wi-Fi has a 60 gigahertz standard, multiple versions of it, 802.11a.c, then AY, and as you probably know, it's not on your iPhone, and it's not in your laptop probably, and it's for sure not in the access point in this room. So you can ask, well, geez, what the heck happened to those wide channels? And so Wi-Fi developed 60 gigahertz as a completely separate ecosystem, i.e. there's an entirely separate standard path and hardware path to implement it. And so that made a very high bar because both the infrastructure and the end devices had to change, and it wasn't mandatory. So what I'm hearing from the Wi-Fi industry leaders is that there's going to be a new approach for Wi-Fi 8, which will repurpose the same baseband hardware and get it as part of the main ecosystem, so that for the next Wi-Fi we will be seeing 60 gigahertz as an integrated part of it. So so for sure I recognize that the past Wi-Fi 60 gigahertz was not a commercial success, but I do see for Wi-Fi 8 that path. On the academic side, I view that our role is a lot of seeing what is possible. And as part of seeing what is possible, you see the limits of it. What are the fundamental limits? What are the problems? Yeah, I view that that we are with sub-terahertz maybe 10 years out. I think that's on your slides. You had it 10 years out, and I think that's a fun place to be, and I think that's a right spot for academics to be. My research, I get funded by Cisco and Intel, and I'm on biweekly calls with them and telling them about curved beams. I feel like, you know, sometimes, why do they want to, hear about the research about curving a beam in a spectrum band that's not going to be in their products for 5 to 10 years? And I view it as very much to see, for them to see what is possible and what is not, should we go there, right? So they're seeing the benefits and the challenges, right? They know if they put a usual phased array, they're not gonna be curving beams, so is that a functionality they want? So they'll know what the cost of doing it is, how much can you curve, and so on. So they get that preview. And then we get the feedback from them as to, if this was to be a path, here are some of the things that we as academics might not be thinking of, and that can also influence some of the problems that we formulate.
Joseph, do you want to add?
We'll use this. I mean, I'll add my perspective, which somehow agrees. My feeling is the following. We base 5G millimeter wave on certain groups or papers saying the channel works. But building a cellular standard is much more than just building a channel. And for example, going back to my comfort zone, we know how the terahertz channel looked 10 years ago, and we're very far from a standard. I have a feeling that maybe in millimeter wave we rise too much. And for example, I'll bring a point. When Edward this morning talked about the near field and how it plays at sub-terahertz, if you look at the size of some antennas at millimeter wave frequencies and make the numbers, you might actually see that in some cases the users are within the near field of millimeter wave towers. That's interesting, and no one thought of that in the past, and maybe that's one of the reasons 5G millimeter wave doesn't work as well as some groups predicted.
Misha, from industry perspective.
Yeah, it's the economics, so you probably don't hear anything new from me there. As you know, Verizon holds a lot of licenses actually, and that is because Hans Vestberg, I think, when he was at Ericsson, took a big liking in millimeter wave. They started deploying actually quite a bit now in local hotspots, so stadiums, etc. Maybe that is causally related to the South Korean withdrawal of licenses, so he was probably preempting a little bit the FCC do the same. I really don't know. I don't have a background on that, but business case is extremely weak, and the telco industry, as we speak right now, until we don't get the APIs going, we are a commodity industry, right? So we are a utility industry, and it's not a bad word. It's just you need to look at it from a utility point of view. When has the water company last time updated your water pipes to the latest you got, right? So electricity poles, etc. So we need to be careful on how we spend the money. So it's an economic issue at the moment. But personally, I think I'm hopeful. As I said, 20 years ago, nobody thought that we would be able to communicate in the mid-bands, and look where we are. Now we're begging for more mid-band, so maybe at some point we'll be begging for more for high band. So give it some time.
Thank you. Questions?
This question is really for the whole panel, and it may be related to the previous question. So many expectations from 5G did not materialize. IoT, factory floor, they didn't happen. Should I be discouraged?
Is that yeah, so as I said before, we don't really have a 5G system up and running to start with. It's kind of 4.9G, so I'm not sure how much you know about the intricacies of all, but currently we're running an NSA network, so you're getting the user plane, really the high bandwidth, but not the control plane. So you can't implement a lot of the use cases we think will move the needle. Whether they will move the needle, I really don't know. A big question mark. I agree with you, right? So market will tell. But generally, I think what we realize is in the odd generations, right, we have a dream, and in the even generations, we implement it. I'm not saying that 5G is bad, but we definitely had very lofty dreams, which will become reality most likely in the end of 5G, 6G. We had very lofty dreams with 3G. We wanted to go mobile internet. It became reality in 4G. We had lofty dreams in 1G. It became reality with phone calls and 2G. So, we need to follow that path. So I'm hopeful. I think it's going the right way.
Judy Jan from University of Minnesota. I have kind of one perspective why millimeter wave is not working well. So we kind of started to do the measurement in Minneapolis and Chicago in 2019 when Verizon deployed millimeter wave. I was not a wireless person. I'm on networking and looking from the application point of view. So we were really excited about 5G and was fortunate that Verizon actually deployed Minneapolis, so we started the measurement. So what we found actually the problem is that actually application cannot really use millimeter wave very well because really if the user turn around or happen to put a hand somewhere, your performance drop dramatically, right? Because the bandwidth is really high. When you drop really big variability. So those are the kind of problem that we're facing. How do you actually make application better use whatever the new capabilities and spectrum, et cetera, right? So this even happened in some of the mid-band. We were doing actually extensive measurement on the carrier aggregation. That's how you can, in the mid-band, how you can achieve a lot of high bandwidth, right? So again, the problem, if user can move, you move from one area to another area, the carrier number, carrier component can drop. Again, impose a lot of variability. The question, how we can co-design application with a lot of physical layer, MAC layer, et cetera. Anyway, so that's just my point. And by the way, Misha, I really appreciate your kind of perspective from industry point of view. I think one of the problems from the research, I mean, this is something I want to ask the industry folks. Today we can only do measurements through the phone, right? So that's very limited. And there's not really a lot of devices. I know the NSF is supporting a lot of research on the wireless, but mostly in the very low level. But for someone like me, I actually want to also run application on this, for example, FR3. We don't have anything we can actually do in terms of actually support applications.
I agree. I think it's a very good point. So, talk to Monisha. I'm not sure she's in the room. They're working on this. So, yeah. With her. Got it. Okay.
Thank you. Marwan.
Yeah, Marwan Kronos, University of Arizona. Very nice talks, guys. I have lots of comments about millimeter wave, but my question, I'm going to turn to mid-band, specifically to 3.1, 3.45. In my opinion, this is probably the most important band right now. I mean, if we end up with 350 megahertz at this region. But, so question from a research point of view, I mean, do you envision, do you envision really significant differences in terms of allowing this band to be shared than let's say what we did with the CBRS? I understand there's the high power issues, but ultimately, if you can still tier it with, radar and, 3-tier or 2-tier architecture, what differences do you envision would be needed in any architecture for spectrum sharing compared to, let's say, what we did for the CBRS?
The answer is probably minuscule. So for those who don't know, CBRS is really protecting the coastal areas. What did not help with CBRS is, apart from the power levels, is that the goalposts move all the time. So the guard bands have actually, the spatial guard bands have changed recently. Industry doesn't like it. We have really years-long pipelines to implement things. That's a big bummer. So we need to make sure that in the 3.1 to 3.45, the whole range there, we really agree on something, we stick to the game plan. That's number one. You're absolutely right. So, that band is occupied by radar, and that's a national radar, and you need to liberate that fairly quickly. And when we ask the DoD, when are you transmitting, what are you transmitting, where are you transmitting, we don't tell you. So, whereas with CBRS, we know what's going on. With that specific band, you have a lot of uncertainty. Does it massively impact the research and the industry pipeline? I don't think so. They're good ways we can actually make this work. Yeah, I think it's a good observation, and we can maybe talk privately. Yeah.
Thank you. I must add, I asked the first question as a researcher working on millimeter wave and putting them in agricultural fields. So I have a lot of hope, but I think it's good to have a reality check. So I want to switch gears a little bit into spectrum sharing and especially licensing within that aspect. Edward, you have unique insight on unlicensed communication. I know, Joseph, you have been working on sharing the spectrum with weather satellites on the terahertz, and Misha, you mentioned the spectrum sharing with government, military, and other sources. So my question is, in the spectrum era 4, as NSF defines it, what should the licensing structure look like? Because it surprises me in the age of AI and dynamic systems that we still have a licensing structure that is pretty rigid. We obviously have some developments over, such as CBRS, which provides some dynamic access to a small portion of the spectrum. But where do you see our licensing and spectrum sharing landscape look like in this new era? And maybe, Edward, we can start with you. From the ultimate spectrum sharing mechanism, Wi-Fi was doing it very successfully in unlicensed band. So what lessons can we learn from there?
Yeah, well, in these higher bands, it's extremely scenario dependent. And so I'm sure Josep will tell you about satellites, and he's done the rooftop links. And so the issues there are quite different than the indoor issues. And so for me, Wi-Fi is almost always synonymous with being indoors. And so we would, above 100 gigahertz, even if there's a radio astronomist, down the street, they're not going to be, we're not going to be interfering with them in this room. So then the issue becomes sharing amongst ourselves. As we go outdoors, the issues tremendously change. Back in the white space days, we were doing commercial deployments in Houston, which had, no, I shouldn't say commercial, we were doing operational deployments in Houston. It was a free network for research. And we had only one TV white space channel, so we were 5 gigahertz for the entire network, entire neighborhood. So you can imagine, and this is many years ago, but you can imagine that didn't go very far. We got an invitation to do a demonstration in Mexico City, which, according to their TV operations, had tens of megahertz open. So we wanted to do a 40 megahertz demonstration in Mexico City. So we found out the contiguous band of 40 megahertz that we could use, set up the demonstration, and it turned out there were actually unauthorized TV channels on every channel. There was no available white space in Mexico City, to our surprise. Our demonstration was not as impressive as it was back in Houston, even in 5 megahertz. So the lesson that we learned from, I'm an experimentalist, so it's what do we learn from the experiments, was that it can be the Wild West once you go outdoors. There can be unauthorized access. There can be, especially as you start to elevate and getting interference from farther away areas. We eventually rebuilt our system so that it would operate in the presence of a TV channel without worrying about them, because in this particular scenario we're viewing, you're unauthorized, so we're not going to try to protect you to watch your TV. But actually it's pretty easy to subtract off a TV channel because it's very deterministic, very easy to know what's going on. So we made all the receivers resilient to that. But my long-winded point is, indoors I think we've got a great story to tell with Wi-Fi, and it'll continue to work extremely well. Outdoors, it's the Wild West. So I'll leave these guys to comment on what's happening next outdoors.
Let me steal this from you. Let's share the microphone. Okay, so
You see who's
we keep,
watching.
yeah. We all keep saying that we'll move to sub-terahertz frequencies because we'll find very large bandwidth. What if I tell you that legally today, between 100 and 200 gigahertz, there are only 12.5 gigahertz of continuous spectrum. There are other chunks here and there, but it's 12.5 gigahertz. You'll say, Giuseppe, 12.5 gigahertz is a lot, no, don't complain. Well, if I don't need those, stick to 57 to 71 gigahertz, you have 14. So we're moving to sub-terahertz for the extreme cases scenarios, and legally today, I cannot find them. You will say, why? Who else is using terahertz? You've been saying that no one else is there, that it's no man's land. Well, not really, right? We have actually Earth exploration satellite services using those bands for very critical scientific information, including, the presence of different water vapor lines that are interesting. What's interesting, however, is that the satellites are orbiting the Earth. They're at least at an orbit of 400, if not 700 kilometers above us. And still yet, they get exclusive access to some of these frequencies. So for example, now that they are not listening, right? Many of the experiments that we've done, including some broadband pulses, may have not been fully within the FCC framework. But no one heard this, right? We do try to get the licenses.
We're being filmed, actually.
Yeah, we're being recorded.
Exactly. That's the whole point. That's the whole
last
point.
time you see him on stage.
That's the whole point. No, I mean, we do have, thank God at Northeastern, we actually have an FCC innovation zone, so we're fine, but not sure at Rice. Just joking. But what I'm trying to say is that there are issues to share the spectrum above 100 gigahertz, and I think that the secret, as was also mentioned before, it's the dynamic aspect of it, right? Satellites are only crossing over Boston every few hours and for a few minutes. Can I interfere with them? Actually, we do. We did the link budget after believing that we could not, and it turns out that we can. So, well, maybe we don't need to share all the time. We just need to strategically, dynamically share, and that's good. Part of that is actually our SwiftSat project, so connection to the program here, and for which during this summer, if FCC allows us, we're going to be trying to interfere to one of those passive sensors at 165 gigahertz, precisely on the International Space Station. We'll tell you next year how that goes. But again, dynamic content, there is no need to protect a band that 90% of the time is not being used.
Yeah, great points. I think maybe let's look at the competitive issue. So I would like to kind of equal the playing field. I'm not sure you know this. The federal spectrum and the license exempt, so the unlicensed spectrum we call in the US, has perpetual licenses. So once it's assigned, that band is assigned, you can't move it. That's it. The IMT cellular community has actually a time frame on it, okay? So which way you go, I don't mind, but make it a level playing field. So my personal view is that everybody should have a time-limited license because it will stimulate innovation, both in the Wi-Fi band, because if you look at, the way how the scheduling works today, the innovation which has happened in IMT is by orders of magnitude higher than what happened in Wi-Fi from a spectrum efficiency point of view, and it's by orders of magnitude higher than what happened in the federal band. So therefore, make it limited, and you will see so much more innovation because there's a real incentive to kind of improve the efficiency of these bands. Second thing is to change maybe on the auctioning regimes as well. So license auctioning could maybe be more incentive auctions, could be more maybe even cashless auctions, escrow type of auctions, and we have considered that in Ofcom on the board actually to see how can we help the ecosystem there. And then the industry, my industry, not surprisingly says, make it as static as possible for SLA reasons mainly, high power, and static for service level agreement reasons. But if we find good solutions, where this could work dynamically, I think the word dynamic is not a dirty word in the cell industry at all. As I told you, we're doing it all the day. But we need to get it right economically and at a fair innovation playing field, if that makes sense.
Any questions on this topic? Sorry.
Thank you, John Valakis from Florida. I wanted to echo, I liked very much all the comments, and I want to build on those. What I hear is the innovations that come in the way the spectrum is licensed, or whether it's finite, whether it's cashless, or whatever that means. The fact that opportunistic, the fact that we're going to have to deal with that we don't have continuous spectrum or dedicated, or that is being used, and therefore there will. Can we conclude that somehow we're going to have to deal with multiple bands and be able to access multiple bands at the same time in order to be able to transfer large data rates? I mean, there's no doubt also with satellites we're going to have a lot of challenges because there will be more and more data transfers from satellites. I mean, what already exists in terms of satellites is just the beginning. We're going to have a lot more satellite services, not just Starlink. I mean, people have talked about that. We're going to have plenty of Starlinks going on. So I would love to hear what your thoughts are in terms of how we're going to use the spectrum in the future. Can we have a service that is going to pay per data rate, or is that possible? Is that going to come? Are we going to have companies somehow cooperate, or is the federal government ever going to say, hey, here is a service, we're going to give you 100 gigabytes of data, per month. Just make sure you use it, and there will be a way of paying for that across the spectrum. So I'm just kind of throwing things out. You guys are hopefully can have thought about those things. So thank you very much.
I'll give a very quick answer. Yes. To all.
I'll give a more long-winded academic answer. So I think multi-band, putting it together is already baked into the Wi-Fi ecosystem with multi-link operation. And I think that's also part of what's going to help 60 gigahertz launch, is it won't be, oh, let's have 60 work and then, oh, there's a blockage because I've got, not everybody's going to be curving beams, right? There's always going to be the best buy access point that's just going to okay, we'll steer here or here, 4, 8 sectors, and then if you block it, you block it. So under multi-link operation, that becomes much more seamless about using different bands and putting the data on the right band at the right time. So I think that'll be baked in. So I'm not losing sleep over the fragmentation above 100 gigahertz that Josep talked about. I think there's some ways around it, although contiguous bands for sure make life much easier.
There is little to add here. What I would just say is that indeed, for all these things to happen, they need to make sense financially, and then we need those wideband designs, including some of your own, when it comes to this. So yeah, wideband hardware that really, I mean, if I could choose, right, I would love to have a radio that can go from 100 megahertz to 200 gigahertz, just randomly, be able to jump around. If financially makes sense, I know that the hardware will eventually come.
Right. So one other question that I have with respect to spectrum sharing and new wireless technologies is the role of AI and machine learning. So if you could each comment on where do you see the role of AI and machine learning in both research and development and eventual deployment?
I touched on it a little bit in my talk, that I think when we get to higher frequencies especially, that we'll have so much rich information about the environment. And so, I mean, there are researchers also who are thinking about putting cameras on an access point. So if you're basically image using visible light a scene, then that could potentially aid the communications. And vice versa, communications can aid an imaging system. So I think that AI is going to play a critical role in synthesizing the sensing problems that we're having moving forward. I think the other big need I see for it is in network management. And so that a little bit touched on that with the control plane for curving beams. But we keep adding functionalities. That's sort of, as researchers, we say, here's a new capability, here's a new functionality. And having a network that can identify its scenario, adapt to the best one in real time with heterogeneous users, some that need curving beams, some that don't. Some are out of the near field, right? This whole room might not be near field if the access point's right here, the edges might not be. And so how to dynamically operate the network and optimize it in the face of all that complexity and the very rich capabilities, I think that'll be a big challenge for AI.
Just to follow up on this, so actually 3GPP in release 18 has standardized 3 use cases for usage of AI. It's channel state information compression, localization, where we have 100x the capability from 20 meters to 20 centimeters. Is phenomenal using AI. And the third one is about beam forming. So it's coming into the standards, it's happening. There's one area I would like to highlight, which I'm very excited about. That is the ability to use transformers, large language model capabilities to understand channel impulse response signatures. What looks very random to us is actually a composition of a room right here where stuff is being reflected off. The same way as a large language model can learn the correlation and sometimes causality between different word structures, it is able to learn the spatial context of the room. There's no difference to that. So suddenly you have a construct which is able to understand what's coming over the next second, 2 seconds, because we are barely moving, actually. We're not really, unless you're on a high-speed train, there's actually very little randomness per se in there. So suddenly you can do things nobody else was able to do. And the first research is coming out for that. It's far too early for industry. But going in this direction is hugely exciting.
I mean, little to add here, and certainly agree. The main challenge when we talk about AI in sub-terahertz or terahertz is the speed at which AI happens. So for some functions that you don't need really real time, that's perfectly fine. For functions that you would like things in absolute real time, I'm not sure how we're going to do that, because if to design and operate my network at sub-terahertz frequencies with the promise of terabits per second, but then I need a couple of seconds to get things set up, I would just go at 2.4 gigahertz steadily with my 20 megahertz. So I think that there are interesting challenges. And again, there are functions in which AI will come in handy because they don't need that microseconds response. That's fine. For some others, maybe not.
Thank you. Again, it's another personal question. When you guys discuss spectrum sharing, I guess you mostly refer to in-band sharing. I didn't hear much distinguish between out-of-band and in-band, as you know, a lot of different technologies or services share spectrum. There will be, it's normal to expect some out-of-band emissions, and things probably will change. What do you think the implication of that? Do you think the spectral mask and all the other things will have to be revisited? Thank you. I guess this is a question for, and probably Misha mostly.
Well, let me start from an industry point of view. Absolutely, the FAA debacle was that, right? So as you remember, the C-band plus altimeters was a problem, because the altimeters weren't updated in the airplanes for 20, 30 years. And therefore, you know, as you switch on 5G at high power, some of that spilled over with the current masks and would give you problems. Now, there have been big ring for from back the NTA, the FAA, and the FCC, until they realized an upgrade would cost $20 million, right? Which some of us in the room probably could write a check personally on this. So therefore, it's not even worth discussing. But you need to really make sure that you get the, you know, that discussion right. And you're absolutely right, the more non-contiguous bands you have, the more spillovers. There's a limit in terms of, you know, if you have a very narrow band, fairly narrow band at a fairly low carrier frequency, you naturally get these spillovers. So we need more innovation from you guys to sort this out, because unless we convince the lawmakers, what I said on my slide, to put everything nicely contiguous in one band, which is unlikely to happen in its entirety, you know, we need more innovation there. So for me, it's wide open. Important problem, though.
Back in, I'll give one more quick comment and then go there. But back in white spaces, we for sure saw that issue on the receiver side. So yes, the TV transmitters were following the rules, but a TV receiver could be made as cheap as you want, and so they were concerns, and they were the ones pushing for a very strict, hard to implement spectral mask on the transmitters, which made it harder to build. The other thing that I often see too is sometimes being unrealistic for the incumbents, in the sense that it can be nice to say no interference, none, zero, but we have to all realize we're all black body radiating right now in every band. So, you know, you say, I'm not supposed to be emitting, I'm doing it. I'm doing it right now. So you can't say zero. Yes.
Excellent. Little to add here. I mean, yeah, out-of-band emissions happen as we get to higher frequencies, harmonics all over the place. And once again, we've invested a lot in trying to get power at the right frequencies, not so much about limiting the power in the not so right frequencies, but absolutely it's there, and maybe not enough emphasis. We forgot to mention it until you asked us.
One last question. Yep.
Thank you. Appreciate the question that John posed. Basically, I think we're talking about spectral efficiency, and AI is, at the peak right now due to the strong and huge progress of Moore's law. The Moore's law brought us here. So in some ways, I understand that spectrum is not growing, especially mid-band, that's it. But computation power due to Moore's law continues to grow. So it makes sense for us to think about computation in exchange for spectral efficiency. So my question is the following. It's arguable that the current AI wouldn't have the success without ImageNet. So what I'm getting at is that train the data for training, and the platform or the ecosystem that encourages, right, the data sharing, and even to a large extent, code-sharing brought the current success. So what do you believe to be, okay, so my question is, how do you think we can overcome the challenges in, say, wireless or wireless networking, where
there is no such ecosystem. There is no such data. Industry is not sharing, say, channel state information management with us. Industry is not sharing, say, even the resource allocation data or satellite data. So Giuseppe was talking about government is not sharing that data with us. So how do we overcome that challenge in order to bring out the real progress in AI so that they can benefit spectrum sharing or spectrum efficiency? That's my question. Thank you.
I'll take this quickly. Yeah, I completely agree. Yeah, and actually, I liked your the similarity you struck with with ImageNet. You're absolutely right. We need that. You'll be surprised to hear that we're actually on the same side as you are, so we don't have that data either. It's the operators who own. We have spot data in our test centers, but we don't have access to any of the globally deployed data sources at all. We need to talk to the operators, right? You need to talk to them. Maybe blockchain solutions could help with the privacy issues. They're very cagey about this. Think also about competition issues. T-Mobile may not want to tell the community what's their status of the network to Verizon and others. So we need to find good ways to anonymize that, make it very confidential type of compute, but we don't have that capability. I'm not sure how best to go about this, but maybe speak to Hans Vestberg or to Ulf or to Egal, to the big carriers. That would be my recommendation, but it's a good point. I agree.
This is a big challenge for working in the cellular space as an academic, and it's one of the reasons I actually work more in Wi-Fi than cellular. Just a quick story. I'll anonymize who the carrier is. I won't tell you who it is. One of my students worked with them when small cells first came out, and the student got to do over the summer some of the first ever small cell measurements. Really cool. We tried to publish it, but the carrier could not publicly admit that there was any handoff that failed, couldn't admit that there was any area of coverage that was anything less than perfect, right? So academics, we love problems and let's solve these problems, but they can't publicly confess to a problem, right? So we didn't publish it, never publish it. There's no small cell papers for me ever. And I can't even show you the data. We tried to normalize it. They said normalize everything, but it's just like if the value's not 1, they didn't want to publish it. So I don't see this changing. I really don't. I don't think we're going to, even if all of us together lobby, they just don't have the incentive. It'll be on the commercial the next day, right? If we publish that, and then it would be, look, this carrier's dropping your calls. Yeah, come switch over. So I'm pessimistic.
We need to work on that. That's a good point.
I mean, because of that, at the very least, the things that we do have, we can put them together in the sense that many groups are generating data, many groups are generating synthetic data. There are initiatives like the RF Data Factory, looking at Kaushik Chowdhury at the end of the room with Tommaso and Francesco, which is the whole point. Look, the data that we get and collect, let's share it in the best way, let's combine it and let's use it. And I think that in this sense, NSF is doing best. Because we have now private 5G networks, maybe we can get something along those lines too, but certainly, it's a challenge, and I think we're trying to solve it, but it's a challenge.
Thank you. And that's a great plug-in for our panel tomorrow, which will be on data sharing in spectrum sharing research, so we'll hope to hear more from that. I want to thank the panelists, and I want to give you one final opportunity for your final remarks, maybe starting with Giuseppe.
Okay, so I'm going to say one thing. In my group, we always say the only limits are the laws of physics. Everything else we can work around. And I think that with the spectrum sharing, it's exactly that, right? Actually, someone will say we can bend the laws of physics, but no, we said that we respect Maxwell, so we're still fine. But that's the only thing we cannot change. So when someone tells us, oh, this is not possible, say why. Is it because of the fundamental physics? Then we have a problem. We may need another set of physics. If it's the technology, that's good, because technologies is what we develop. And if it's the laws, if it's the policy, well, actually that also should be good, because discussions, intellectual discussions, are the ones that can lead to changes, and events like this is what this opens. So again, the only limits are the laws of physics.
Thank you.
I guess maybe to piggyback on your very nice limits statement. When my students and I are brainstorming about what to work on, they're often feeling like they're in a little bit of a box by the spectrum rules and by the standards. And in the Wi-Fi domain, I tell them the version that's there now will probably be done by the time you graduate, right? New Wi-Fi versions are coming every couple of years. And so I tell them, you're not constrained by standards. You're also not constrained about spectrum policy either, in the sense that that will change. And if you show something great that we can do with spectrum under a new rule, well, that would be a wonderful result. And so to open up the playground, I think that's what academics should be doing, and show what is possible under a completely new standard and a completely new regulation. And of course, that gets us a little farther away, potentially, from where we are today, but it at least gives us a potential new destination. And then we, the industry and everyone else, standardization will decide if we want to go there.
All right, so, my closing is maybe to thank you that, you listened to me today, and thank you for addressing, hopefully, problems I laid out to you. These are very, very pertinent problems to move forward. You know where I am, so you just email me, and we can jump on the call. I'm very happy to be that proxy between the academic ecosystem and the industry ecosystem, and I'm offering my help also to sort out the data problem. Actually, I just realize it's a very fundamental problem on why there might be a real innovation bummer right now. So, and we're on the same side. I didn't know you too have that problem. So we'll need to solve that. I'm a little bit more optimistic that we can do it, but I'm here to help, and thank you for listening today. Thanks.
Thank you, Michel, Edward, Joseph. Thank you.